We last talked about random variables and this little notation for their probabilities, at least for discrete distributions. We'll get into what we mean by discrete a little later. Well, discrete just means you have these individual possibilities. You don't have continuous random variables, continuous arguments. But anyway, here's the notation. P for the probability, X means for that random variable X with some kind of argument. In this case, the possible arguments were 0, 1, and 2, which means that the possible realizations of the random variable. Here's how we would say it in general. P for the probability, X for of that random variable. This is big X, capital X. Little x for the realization of that random variable, meaning what you would get in any one outcome or event. So that's the notation for a single random variable. Joint probability, now we're talking about more than one random variable at a time. Let's just talk about taking two at a time for right now. If you had to spell out all their possible outcomes, in this case, it would be this 5 by 5 matrix of numbers. And I'm going to say we're given those numbers. That's the probability distribution. Somebody gave us all these P of X, Y's. So here's the notation for the joint probability. XY here doesn't mean the product XY, it just means variables XY. And it would have two possible realizations. This is for X is a 3 and Y is a 4 here. Those numbers in this case could represent, if we had two balls each of 5 colors, as noted here, in an urn, and X is the random variable of pulling what you get on the first ball you pull out, and Y is what you would get on the second ball you pull out. But we're not going to go through all that combination permutation stuff. We're just going to take these numbers as givens, and then we're going to see what we can calculate from that. If you'll notice, if you add all these up, you get 1, which is good. So each one is greater than or equal to 0. That satisfies an axiom. Add them all up, you get 1. That satisfies an axiom. If I added up over all the x's, all the possible x's, I get a number, and it's the probability of y. So if I add up all these probabilities that x is any of the colors, I get 1/5, and that's the probability that y would be black. Actually, the random variable 1, because we're dealing with random variables now, not colors or something else. We call those the marginal probabilities now. You could just call them normal probabilities or unconditional probabilities, but in the context of a joint probability, we call them marginal probabilities. We can calculate them from the joint distribution. Remember, we talked about independence when we were talking in terms of sets and events. When we mapped it all over to random variables, here's what it means. This joint probability is equal to the product of the individual probabilities. If they are independent, this is true. This is true, they are independent. It's an if and only if thing. And that has to be true for every permissible value of x and y. If you look at this, it is true for every value. The px and py are 1/5 in every case. Multiply them together and you get 1/25 in every case. It holds in every single case. So this X and Y are independent. Conditional probabilities also carry over from the set theoretical treatment of probability to these random variable probabilities. Here's the notation for the conditional probabilities of these random variables. I left off the arguments here, but I could put an X, Y with the line between them as the arguments. But these are basically formulas that we get because they carried over from the way we calculated conditional probability before. Now they hold for random variables. This would be a similar matrix of numbers, a joint probability distribution. In this case, in the first case, after we drew out the first ball, we put it back in, shook up the urn sufficiently before we drew out the second ball. In this case, we don't. Once we draw out the first ball, we leave it out. We're not going to concern ourselves with that part of the problem. We just take these numbers as givens. And now you see that that test for independence doesn't hold for any combination because all these individual probabilities are still 1/5. You multiply them together, you get 1/25, and that is not true in any case. And all it took was not to be true in just one case. So this is a case where X and Y are not independent, they're dependent. It makes total sense. If you take out a green ball in the first draw, you've only got one green ball left for the second draw. And also, from these numbers, you could calculate these conditional probabilities. Here, for example, the probability that the second ball Y is a 3, meaning green, given that the first ball, X, was a 3, also green, you can calculate it. PXY 3, let's see, 3 is 1/45th, and PX of 3 is this number here. Use the formula, it calculates to 1/9. So we could calculate a lot of stuff from the joint distribution. Similar calculation if what the second ball is a 3, Y is a 3, meaning the second ball is green, X is 4, meaning the first ball is yellow. Calculated it, and we get 2/9. That kind of makes sense. The probability of getting two of the same color wouldn't be as good as getting probability of different colors because you took one out after the first draw. Anyway, that is the concept of joint distributions. Next, we're going to get into continuous random variables. Everything we've been doing up to now is things like coin tosses, card draws, balls in an urn, stuff like that. Anyway, that's that.